Okay, so this is continuity equation for the incompressible flow. All right, this is for compressible flow, incompressible. Okay, but these two equations are defined in Cartesian coordinate system. 它是定义在这个卡氏坐标。If your system is operating in a cylindrical coordinate system, 在圆柱坐标就是圆管那种情况 ，your continuity equation look like this one. All right. If you define in the spherical coordinate system, 在球面坐标的时候，这个时候你会用这个 continuity equation 这个方。当然，这个各位可以看出来，you can see that the low is still inside of the parentheses. Okay, so in these two equations, they are defined for the compressible flow. Okay, if you operating in the incompressible flow, you should take this law outside of the differentiation of 3 parameters. Okay, 你就应该把那一个微分要拿出来，对吧？把这个 law 就拿到这个微分外面。Okay, alright. Here is for turbulent flow. You find the turbulent flow is very similar to our case, our continuity equation. Alright, this one. This continuity equation for the turbulent flow is very similar to the laminar flow. But here, laminar flow, UVW is a local velocity. There is no fluctuation. Here, in turbulent flow, we define that the UVW is given the start over each velocity component. It means that these 3 velocity components are mean value. Okay, so the very slight difference in the expression. But in general, the general form is look very similar each other for the turbulent and laminar flow in the continuity equation. 在连这个 continuity equation 上面的 turbulent flow 跟 laminar flow 基本上是一样，差就差在这个地方，在 turbulent flow 的它是一个平均值。Okay, now we use the continuity equation and the equations of motion to solve some of the problem. I just talked about one section. There's another 3 sections. You have to read by yourself because there are a lot of material. Okay, we have to keep the pace of our course. We talk about the flow between parallel flat plate. 就这个流体在2个平行的板子 ，OK， 平行的这个板子 ，OK。Let me give you the idea, OK。Two parallel plate. One plate, the up plate moves with the velocity we call the v. The low plate, they keep stationary, 就是在静止状态。OK, we use the equations of motion. 我们会使用这个运动方程式 to solve the velocity distribution. Is look like this. This is v-bar. This we call the simple shear flow. Or we call it coil flow. We often use this kind of the mechanism. Use the 2 parallel plate. One plate is the moving velocity v, relative to the other plate. To create the simple shear flow, to measure in the chapter 3 or 4, we talk about the oil viscosity, right? We created the flow, the oil flow to be the simple shear flow. Now, if we have the simple shear flow, we can use this kind of instrument to obtain the viscosity, oil viscosity. So this is the example. Okay? But in the next section, in the later chapter, we'll talk about the bearing, especially the thrust bearing. Very important, okay, in the machine design, okay? The low plane may be also keep stationary. But the upper plane is to make a very small inclination angle. This angle, almost about 4 degrees. So this degree is very, very small. So in the appearance, 从外观看，这个面跟这个面 almost in parallel。你的很多的轴承啊，大的机械轴承，这种就是指挥轴承。The inclination angle is very, very small. So in appearance, you will find that the upper plane and the lower plane almost in parallel. Okay. They have two kinds of the geometry. The flow from the left movement to the right wall, okay, to the right direction. This is this instrument, and then another is this instrument. Which one is can be used as the thrust bearing? You apply load over the upper plane. Load for the upper plane. This inclination angle very, very small. Okay. Then maybe you have to. We will talk about the later in the later chapter. We'll talk about this one and this one. What's the difference of this one? And then these two are different from this one. We say here in parallel plane, they have the velocity distribution, but no particle pressure. 它不会产生这样。如果两个平板时，不会产生这样。Is for two parallel plane in motion, it's impossible to create a particle pressure inside of the floor if two planes are in parallel. But to this one, these two. Let me talk about this one. Okay, the plane is inclined from the left-hand side to the right-hand side with the this value. Okay, so this is this left-hand side. They have the maximum fin thickness. The fin thickness is the largest one, and this is the smallest one. If we put this one, this kind of inclination, and the flow is from the maximum fin thickness flow into the direction to the minimum fin thickness. In this case, we have used the Reynolds equation to solve this kind of case. We have the particle pressure created. Can be created in this case. Okay. We can solve the Reynolds equation, obtain the pressure distribution. This pressure, given the integration over the area, can balance the applied load L. So in this case, particle pressure can create it in the flow. But to this case, from the minimum fin thickness to the maximum case, if we flow is from the minimum fin thickness to the maximum fin thickness, in this case, the angle even the same. We don't have any pressure, no particle. No particle pressure exists. So in this case, the bearing is this one. This is bearing. This is not bearing. 因为这个角度很小，往往装的时候，你装颠倒了。This is a very bad experience for the type of 排电，然后的 electric generator, okay. They just have the thrust bearing. They just reverse the inclination angle, cause a large damage of the machine. So if we have an inclination angle, there may be a thrust bearing, maybe not. If we wanted to have the bearing function, you have to put your maximum side and the minimum side. It's just in this. Your flow should be enter the maximum side and then out of the minimum side. Otherwise, it is not the bearing like this one. Okay? So you will have the picture. There's two parallel plate over one plate with a small inclination angle with respect to the other one. It's totally different. Okay? If we want to do a bearing, we should be the upper one, not the lower one. Okay. All right. This we call the wedge effect. We have to talk about it in the first and the second chapter. Wedge effect. Okay. All right. So this is we just talked here. We just talk about the two parallel plate. But the upper plate with the UA, the low plate is other rest. Right? Now we have the equation motions look like this one. Here, dp dx is the mean x here. X in our bearing system or in our flow mechanical system, we define the x to be the flow direction here, right? Okay, and then y direction is the x direction, y perpendicular to the x direction. Okay, mean that this is flow direction, and then another direction is just perpendicular to or normal to the perpendicular to the flow direction. Okay, so this is y direction. What is the z direction? The fin thickness direction. Okay, this is z direction. Okay, so here the velocity is vary with the z direction. Okay, and then the pressure gradient. This is the pressure gradient. Here, dp dx equal to, now we have the pressure gradient. This is the pressure gradient. Here we have the U. If two parallel plate, the upper plate with the UA, you'll find that your velocity look like this one. I will talk about, I will solve this equation, obtain the velocity profile. You'll find that your U is x direction. This is u. U is z direction. U. This is x. This is z. All right. Z is the fin thickness direction, and then x is the flow direction. And then we obtain the velocity. We call local velocity. We call the u of z. U is function of z. So in this case, u is function of z only. In this case, partial 平方 u, partial u, partial z squared. This term, u is function of this one. So we obtain the partial square u, partial z squared is also function of the z only. Right? This is the z function. So we take the two differentiation with respect to z. We obtain the function. This function is still a function of z. Right? So this term is function of z. But our experiment, we can measure the pressure variation along the flow direction. Right? We obtain the P is a function of x only. No, x and y only. P is a function of x and y only. So this P, take the differential equation, we obtain it. Because our P is a function of x and y, not a function of z. So dP dx shall be the function of x and y. So the right-hand side, dP dx, is a function of x and y only. And then our left-hand side, u is z function. Take the two differentiation with respect to z. In this case, we still obtain the z function. So the left-hand side is a z function. The right-hand side is x and y function, right? They are equal together. It's a mean that this term is constant. So the right-hand side is an xy function, and the left-hand side is z function. They are equal together. There is only way that these two terms should be the constant value. It means that this is a constant value. So it is a constant value. Then we have to integration with respect to z for the left-hand side. In this case, we obtain the general function of this differential equation to be this one. This is the general solution of this differential equation, right? Because we take it as the constant. Okay. So this is why from here we can obtain this one, because the dP dx is function of x and y, and then for the partial square u, partial g squared, this is function of z. All right. The coordinate different, but they are equal. It means that these two terms should be the constant. So in this case, with integration with respect to z to obtain u, we can take this term as the constant. So we obtain this one. Right? Okay. So this blue mechanics, they have taught us that you have to identify why from here the integration obtain the general solution to be this form. Because this term actually it can be considered to be a constant. I assume it's constant because the left-hand side is the z function. The right-hand side is the x and then y function, right? They are equal. This means that they are constant. Only the constant we have the equivalence of this equation to be satisfied. Okay, all right. Then we have the general function. Then we have the coefficient should be determined, right? So these two undetermined should be obtained by the boundary condition. The boundary condition is the bottom one, we have the velocity. The upper one, we have the velocity, we call the UA. The bottom one, we have the velocity equal to 0, right? So with these two boundary conditions and then this general solution, we obtain the A, and then obtain the solution is this one. This is the velocity solution. This is velocity solution. Okay, so this solution, let us look at this equation, all right? This is u, just the velocity, local velocity in the x direction is this u, right? They have two terms. This term is related to the dp dx. This we call the partial flow. We have the u, means that we have a flow motion. We have the flow motion, right? So how to make the flow move in one direction? Here we move in the x direction. They have two terms. They have two factors. One factor is related to the pressure gradient, not the pressure. So pressure gradient will allow the flow from the high pressure move into the low pressure. This we call the partial flow. Another is related to the UA, H is the strain rate. Is related to shear strength. Related to the shear strain rate. Okay, so in this case, this term is we call the Coulomb flow, Coulomb flow, right? So this equation, this one is related to pressure term. This is related to the shear rate term, shear rate term. Pressure term, pressure gradient term, we call the partial flow. It look like this form. This is partial flow. This term, when you plot the profile, it look like this one. And this term is like this one. So your velocity is the summation of these two terms. It means that your profile with the left one plus the right one. So these two combined together obtain your profile is look like this one. This plus this one, your profile may be looking like this one. Okay. So this is in our case, we have a profile is this plus this one, right? Okay. So the profile is looking like this one. If we have a velocity like this one, this is a push flow, this is a correct flow. I have repeated many times, right? So if you want your flow moving in one direction, they have two factors. One is the pressure gradient. One is the shear strain rate. Okay. So one is caused by the partial flow. One is caused by the Coulomb flow. Okay. So in our lubrication area, they always just two kind of flow inside of our flow. Okay. So this combine this one obtain the final velocity profile. This looks like a product in the board, like this one. So when we have velocity, we can determine everything. Here, du dg, we have obtained u. Du dg obtained this one. Okay. Then the shear stress, shear strain rate in the lower one and in the upper one, we can have evaluated, use this equation to let the z equal to 0 obtain the shear strain rate at the low pressure. This is in the upper pressure. Alright? We have the shear strain rate in the low one, in the upper one. These two differences only in the first term. In the first term here, dp dx may be here, dp dx may be positive, may be equal to 0, may be negative. Okay. So this maybe have a dpdx may be positive value, may be equal to 0, may be the negative value. Okay. So here, the shear strain in the low pressure and in the upper pressure, the difference is the low pressure with the negative sign. Here we have the positive sign, and then the last term in these two equations they are equal. They are the same. Okay. the other side. All right. So shear strength rate in the lower one, in the upper one. Okay. And then we can evaluate the flow rate. The flow rate. This is a fixed station, is moving in the UA, right? Okay. And then the have the length, we call the L. We have the width, we call the B. Okay. All right. So in this case, the flow rate per unit time flow over the system can be evaluated. Okay. Now we define the Q prime, okay. Because the flow rate is dependent on the velocity distribution, also dependent on the width and the length of the flow of the barrier, okay. Now if we evaluate the flow rate based on the unit length, unit width. Okay. Originally, it's based on the flow rate is based on the width and the length, right? But we evaluate the unit width, the flow rate for the unit width rather than the B value, rather than the B width. Okay. So originally it's B width, but now we define the Q prime is for the unit width. So this is the unit width is mean that it's one unit width for the B direction, right? So this we call the volume flow rate for the per unit width. We will have the U times the dg, and then take the integration from 0 to the fin thickness. We call the local fin thickness. We call the h. Okay. So it is the OH UDC, all right? So this flow rate is defined for per unit width, all right? So Q prime is this value. 我们的单位的这个宽度的这个流力，我们会给它直接这样得到。所以我们这个积分，我们没有得到这个 dy 的积分，没有 y 方向，我们不给它做积分，因为 y 方向我就把它当1了 ，OK？ 所以这样直接这样得到的结果叫 Q prime。Q prime 你的 U 已经得到了上面那个方程式，你有 U 了，你把它带进去，然后你就可以得到这个东西，你的 Q 就得到这个值。对不起。好，你就把它这个 U 那上面的式带进来，然后积分以后你得到这个值。So the Q prime for unit width obtain the two values. One is related to the pressure gradient. One is related to the pressure gradient. As I have mentioned earlier, that dpdx may be positive, may be negative value, also may be 0. Okay, so this value is positive or negative, totally depend on the dpdx sign. 就是你 dpdx 可能是正的或负的或等于0。所以这个值有可能正，有可能负 ，OK， 有可能等于0。这个是 quick flow， 就是跟线旋率有直接关系的，它就跟这个线性的速度有关的这一项，我们叫 quick flow，OK。So this quick flow is related to the linear relationship of the velocity profile，OK，right。So combine together， 我们把它加在一起的话，我们有这一个，在这个两个平行面之间的速度分布。有这个4种 case， 有这个4种 case。Okay, we have the one of the 4 kind of the profile in our flow channel. Okay, the first one is look at this one. This one let me talk about dP dx. dP dx 是什么意思？我这样流过来，这是 x 方向，这边是 x2， 这是 x1， 我们沿着这个方向跑。The flow direction is from x1 to x2, right? And in this case, if P2 larger than the P1, the pressure in here is larger than this one, then we have a dP dx is positive, right? It means that when I run forward, I find that in there the pressure is larger than the position I located. Okay? In this case, when I run forward, I find that they have some of the force against me in the running. 就是我要往前跑，你那边压力大，你又把我 push back. I want to go forward, but the high pressure in front of me will try to, against me, allow me to move forward, however, more difficult. Okay, so in this case, we call it is a reverse flow, right? So dP dx larger than 0 in these two cases. You'll find the pressure when we move from the right wall, right hand side to the left hand side, from the left hand side to the right hand side, you'll find that in the flow in front of the how can I say dP dx 大于0. Okay, if it's larger than 0, it means it is a reverse flow. Means that the flow move right hand side, but you'll find that they have meet the high pressure in front of this pressure, in front of this velocity. So in this case, some of the area, if the strength of the energy of the flow strength energy is not enough, then you will find that the flow, the upper one move forward, but in the lower one, a portion of the flow will move backward. 也就是你在这个地方你的能量不太够，那这边的压力比较大的时候，你往前跑的时候，它没办法往前跑，于是这个流体怎么样被压回去？所以这种情况我们叫做 back flow。or reverse flow. Okay. So dP dx if it is larger than 0, in this case, you mean that they have the backflow in somewhere of the flow region. Okay. Here we find that the flow is moving left hand side. Okay. The upper one is still continue moving right hand side. Okay. So this we call the backflow. Alright. In this case, we take the 谢宣率，我们把那个谢宣率给它算一下，算底下这个点，这个点它就对这个 profile 做斜率这个样的斜率，这边的斜率，上面的是这边的斜率 ，OK， 这边的斜率，底下的这个斜率 ，the low one, the slope or the 谢宣率 is negative because the 斜率是这样的方向 ，right？ So if you value your 谢宣率 at the low one, we have a negative value, okay? But in the upper one, the slope is positive value. The slope positive value is mean the 谢宣率 the value at the upper one is the larger than 0. Okay. So this is we have the backflow. Okay. The second is that we still have the reverse flow. The dP dx is larger than 0. But in this case, the dP dx this one may be smaller than this one. It means the dpdx for this case may be smaller than this one. 我们的这一个压力批复大一点，但这个 case 可能小于这个 case。这个时候，我们的 pressure， 我们的这个速度的 profile，our velocity profile will look like this one. Okay, this one is look like this one. The second case. Here we have the UA, right? It looks like this one. And this velocity profile is tangential to the vertical line. This vertical line. And this velocity profile, after the low one, is tangential to this one. And then the slope of this one, we'll find that is, it means that this profile is tangential to this vertical line at this point. This point in the fluid mechanical we call the separation point. 分离点。All right, separation point. Okay, so separation point is that after this separation point, they have a backflow. 就从这个点以后，后面的区域它就会发生 backflow. Okay, so this profile is tangential to this vertical line. 这个 profile 跟这个垂直线在这个地方是相切的。Okay, so it occurs in the reverse flow behavior. Okay, so dpdx larger than 0, and then du dg in this one equal to 0, right? This is small than 0 because the slope is negative. But here the slope is 0 because this curve tangential 就跟这个垂直线它是相切的。So this is 0 rather than the small than 0. Small than 0. Okay. Here, upper one is a set. It's a positive value, so this is positive. Okay. For the 泄水呢 So this is the second case. So this is second case. The third case is like the dpdx. It's a negative value. dpdx negative value we call the forward flow. 顺流。什么意思？移动的时候 you move in the x direction. Here x2, here's x1. P2 then P1, right? P2 smaller than P1. In this case, dp dx is a negative value. All right? Here we call the forward 就顺流、顺风。顺风的时候 you'll find that the profile become more, become more fat, okay? You'll find that, the profile in the middle region become large, okay? Because this is we call the favorable case, like you running on the ground, all right? If your wind, the downwind or reverse wind, if this downwind is favorable for you running, for the running fast, is favorable for you to run faster. Okay. So in this case, dpdx is smaller than 0. 如果它小于0的时候，这是顺流。顺流的话，这个值是正的，这个也是正的。在这个地方 dpdx if it is larger than 0, then this term is small. This term is become negative value. This is positive value. So you will find the forehead become thin. 就变得比较薄。Okay. If this case dpdx into negative value, then this value is positive. Positive plus positive value. So these two values, their summation together will become more a large value. So your profile become fat. Okay, all right. So this case is also set. But here, this maybe is changing to be the this value, small than 0. Okay, this one is wrong. You change this dp dg. Okay, g. It should be larger than 0 here. Should be, I don't know why they have the 0. Okay, it should be larger than 0 here. Here, because g equal to h is under this form, then du dg, the slope, is 0 or larger than 0. So I hope that you change this one. Originally is g equal to 0, change it to be the larger or equal to 0. Okay, in here. Right? This one. Because the slope may be 0. Okay. Maybe 0 is mean that the profile is look like this one. Here is vertical. Okay, we have a right angle other than here. In this case, it's 0. If it's like this one, then it's larger than 0. This case is partial u, partial z, larger than 0. Okay, here, this one, we have a right angle, then partial u, partial z, equal to 0. Okay, so here, maybe large or equal to 0. So please add the large sign over here. Large or equal to 0. 这个地方可能大于或等于，在这个地方 ，OK， 在这个地方它不太一样，在这个地方 is negative slope, right? The upper grade, the slope is negative, so here is less than 0. So this the velocity profile. One of the four profile maybe existent in our lubrication case. It depends on your bearings design and your operating condition. Your operating condition and your bearing design will cover your profile. One of these four kind of the profile, maybe in your flow channel, in your flow behavior. Okay. So this 我们经常会碰到的这个4种的一个 profile 的形式。你要知道这个压力。But here, we just solve the velocity profile. We don't solve the pressure distribution. Why? That's because our equation motion is used to solve the velocity only. 我们只是用来求速度。So you use the equation motion to solve your lubrication problem. I think it's meaningless. Why? It doesn't make sense. Why? Because you solve the velocity profile or velocity distribution in your flow behavior. Okay. But the velocity profile is not we need. We don't need the velocity profile. We need the pressure distribution over our flow. 我们要的是压力在我们流场里面的这个分布，因为我们要得到一个这个负载的一个能力啊，所以你用这个速度的profile你用那个运动方程式去求你的问题的时候，你很难得到这个压力的分布。还好这个问题没有压力的这个出现的一个可能性，因为两个平板 ，OK， 所以这样的一个情况之下的话。we use the equation of motion, we can solve the velocity distribution only. We cannot obtain the pressure distribution. we obtain the velocity distribution, but we cannot obtain the pressure distribution. But pressure distribution are the real one we want, alright? So in this case, we try to change our equation of motion to be the Reynolds function, Reynolds equation. Reynolds equation is developed to solve the pressure distribution rather than the velocity distribution. Okay, so now next chapter we turn to the next chapter. We call it chapter 7. Is just used to develop the Reynolds equation. The Reynolds equation provides us to solve the pressure and the fin thickness distribution. Okay, rather than the velocity distribution. 所以我们在得到一个润滑的问题的时候，我们往往不用这个运动方程式啊。We don't use the equation of motion to solve our lubrication problem because we don't need to solve the velocity distribution. We need the pressure and the fin thickness distribution. This is just two parameters we need. Okay, so that is we turn to try to change the equation of motion to be the Reynolds equation in the chapter 7. Okay, the rest subsection 下面的几节啊，它有谈到一些这个其他的一些流程 ，OK， 一些流程。那个谁要帮我弄下一站？这in the subsection, you read it by yourself, okay? All right? So I just give you the example that the use equation of motion to solve our velocity distribution in different flow field, okay? But I have mentioned, mentioned many times that the equation of motion is used to solve the velocity distribution, but the velocity distribution are not the real one we need. We need to obtain the pressure distribution in our flow, all right? And obtain the fin thickness, okay? So that is, we turn to the chapter 7. In chapter 6, we don't have a homework, but you have to read it here. Now we turn to the chapter 7. We try to obtain the Reynolds equation, given the derivation of the Reynolds equation from the continuous equation combined with your equation motion. Why we need this equation? I will repeat many times. We needed to solve the pressure distribution and the fin thickness, local fin thickness distribution in our case. All right. So the first one, how to obtain the Reynolds equation. The derivation detail is just in this chapter. Okay. Now, before we develop the Reynolds equation, we have the equations of motion. The equations of motion, the general equations of motion is every time we have four kind of the force in this equation. But in the lubrication, our geometry and the flow behavior, maybe not all the term in the equations of motion. They are same of the order, they are have the same magnitude order. 也就是说，我们在运动方程式里面，有些项其实比起其他的项是小很多的。Okay, so if you use the equations of motion to solve your problem, you'll find that it's very difficult to obtain the right solution. And then sometimes you have a in confront of the divergent solution problem. 也就是你容易碰到你在numerical solution 你有这个发散的问题。So if you use the general form of equation motion to solve your problem, you'll find that some of the term may be small, much small, or much larger than the other term. In this case, you solve your equation, you'll find that your solution are wrong, or it's very difficult to obtain the convergent solution of your differential equation. Okay, for example, this is the ordinary differential equation. But the coefficient of the second term is much larger than the other terms. If you sum this y solution without neglecting this equation, without neglecting this term, if you solve it directly, you obtain your y solution. The solution is wrong. OK. 你知道，如果你今天直接去解到这个 y 的 solution， 这个地方有一个系数 ，this coefficient is much larger than the other one. In this case, you'll find your solution. You can obtain, but the solution is wrong. OK. If you like this one. This coefficient is much smaller than the other coefficient. If you solve it, you obtain a solution. It's very difficult to convergent. Very difficult to be the convergent solution. 也就是说，你不容易得到一个收敛解。OK， 好了，各位不相信，你回去解看看，解了以后用电脑去带那个纸保证你错掉。OK， so in the equations motion.